Okay, this video is going to be used to give some concrete examples of what is sometimes called the net change theorem in calculus, where we have a function f and its derivative f prime of x, which can also be called the rate of change. So this theorem says that when we have a change in x for the original function from, let's say, 2 to 6, then there's a corresponding change in the y value, and that the definite integral from a to b of the rate of change function will give the change in y for the original function. Now what we're going to do is use a specific example here to take a look to see if we can understand exactly what's happening. If you think of the distance formula, not the distance formula, distance equals rate times time as an example, I'll write it this way. And put a specific function in here. That kind of is like a distance equals rate times time problem where the rate is 2 miles per hour. Maybe somebody's walking at that rate, and x is the time. So in this example, the red line represents f. And here we're saying that as we traveled from time 2 to time 6, that was the change in the distance. We went from 4 up to 12, or a distance of 8. Now I will make mention of the fact that if we actually found the derivative of that function, we would just get a constant function 2. And so what I've done down here on this graph is actually graph the derivative function, which happens to be a constant, the line y equals 2. And so if I look at the same interval going from 2 to 6, from 2 to 6, the area under the curve, this area right here, happens to be a rectangle because the rate of change function is constant. And this distance right here will always be 2. That kind of corresponds to the rate of change portion of the original function. And this distance right here from 2 to 6 is kind of a slice and represents the time that we traveled from 2 to 6. And the area of that rectangle is actually, this is a distance of 4, this is a distance of length of 2, so that's 8. And that matches the change in y. And that's what the net change theorem is saying. Now I'm going to go to the Desmos graphing calculator and just show you where I got that picture from. Here's the original function f of x, which is this red line right here. The derivative of f of x is this blue line. And then I let a equal 2. And y equals f of a is this dotted line right here. This is just to help give a picture of the starting y value. B equals 4. So f of b, y equals f of b would be this line. So in this case, the change in y is from 4 to 8, between the dotted lines. And the area under the rate of change function from 2 to 4 is this, the area of this square right here. which happens to be 2 times 2, or 4, which is also delta y, f of b minus f of a. Now watch what happens if I slide b to the right. Change in y increases. There, whoop, I wanted to go to just to 5. Now the change in y is 6, and guess what? The rate of change is still a constant 2, but the width of the rectangle has changed from 2 to 5, so it's 3. 3 times 2 is 6, and of course this will keep going this way. So that's what the rate of change theorem is. It's pretty easy to see when the rate of change function is a constant. Let's just tweak it a little bit and change this to x squared. Now the original function is a parabola, y equals x squared. I got from 2 to 6. Let me bring this back to 2 to 4. Okay, so now we can see that the change in y is from 4 up to 16. So the change in y is 12. Question is the area under the rate of change function, which happens to be the line y equals 2x, does that equal 12? And this happens to be a trapezoid. Of course, when you're doing calculus and figuring out how to evaluate a definite integral, we did Riemann sums, where we divided this area into little rectangles, smaller and smaller, for delta x, and then kind of took the sum of the areas of those little rectangles. In this case, though we can actually compute the area, because this is a trapezoid. So the bases are 4 and 8. This is a length of 8. This is a length of 4. So the area of a trapezoid is 1/2 the height times the sum of the bases. The height is 2. Half of 2 is 1. 8 plus 4 is 12. 1 times 12 is 12. That matches. I could make this smaller. So now the change in y is only 5. This is half, or this distance is 1. Half of 1 is a half. Half of 10 is 5. So, of course, if we change this to x cubed, now the rate of change function is 3x squared, another parabola, but now the area under the curve, under the rate of change function, we cannot compute exactly like we did with the rectangle and the trapezoid, because one of the boundaries is the side of a parabola. But this still gives you the basic idea that that area, let's see, that goes all the way up to 27. How about if I take this to 0 and this to 2? Up 2. Okay, so the change in y is from 0 to 8. So what we're suggesting here is that the area under the curve, under the rate of change function, will also equal 8. But we can't compute it exactly using geometry. We have to use calculus. Let's go back to page 2 here. on the whiteboard. Here is y equals x squared. The blue line is the rate of change function, just to summarize. And what the net change theorem says is that for the original function, a change in y can be calculated by calculating the definite integral for the rate of change function, which is the derivative, of course, of the original function. So hopefully those little pictures help give a better understanding of what that theorem is all about. I did want to go back here and change this f of x to e to the x and make mention of the fact that e to the x is the one function that has itself as its rate of change function. So as we increase this, the area under the curve again equals the change in y, but the point I wanted to make is that the red and the blue graphs overlap each other because the original function is e to the x, the rate of change function is e to the x. Kind of cool. Okay, so with that I'm going to end this video and hope that helped clarify some things about the net change theorem.